Hi everyone, and welcome to iScience, interactive science education. We're coming to you virtually from the Coweta County School System Central Office, and I've got a few demonstrations I wanted to share with you today. So before we get started, I've got two rules that are very important. Rule number one is don't try this at home. I've got a lot of stuff up here that looks like stuff that you have at home, but your folks might get upset with you if you do some of the stuff with your stuff that I'm doing with my stuff. I'm a trained professional. I've been doing this for a long time, so please don't try this at home. And then rule number two, I am not a magician. Nothing I do up here is magic. Everything I do is science. So rule number two is it's not magic, it's science. So let's get started and try out some things, okay? First thing I want to start off with over here is our Erlenmeyer flask. And in the bottom of the Erlenmeyer flask, you can see that there's a little pill looking thing rolling around in there. That pill thing is a magnet. And when I put it on top of this hot plate has a stir mechanism in it. And when I turn the switch on, a magnet in the top of the white plate will turn and cause the magnet inside the flask to turn. Now you'll notice as I speed it up, you'll start to see a vortex form. A special kind of vortex. So it looks like a little water tornado. That is actually a toroidal vortex caused by a spinning fluid. You're going to see a lot of those today. So what I'm going to do now is I'm going to add some of this stuff. This is a universal indicator. What universal indicator does is it indicates the pH of the solution. I can't tell whether this solution is acidic or basic or what just by looking at it. So what I'm going to do is I'm going to put some of this in there, and it's going to help us see what the pH is. pH of 7 is green, and if you'll notice, we got a little green color. All right, so then what I'm going to do next is I'm going to add some of this stuff. This is milk of magnesia. All right, milk of magnesia you might take if you have a stomach ache, and what it does is it helps to neutralize the stomach acid. It's the opposite of an acid, and chemists call that a base. So this is basic, all right? So when I pour this into our solution here, we should see a color change because this is neutral right now, but it's going to become basic. And you can see the color change. So it turned from a green color to a kind of purpley color. All right, now I'm gonna add some of this stuff. This is just plain old vinegar, all right? And vinegar is in a class of compounds called acids. You know acids, you run into them every day. Lemon juice, orange juice, tomatoes, vinegar. Vinegar is an acid, and it is the opposite of a base. So what I'm doing now is I'm gonna add it to our solution, and something interesting is gonna happen. Here we go. 3, 2, 1. So now you see the color change is happening. That color change that's happening there indicates that this solution is turning acidic. So the orange and yellow color that you see here indicates that the vinegar is interacting with the milk of magnesia and turning everything into an acid. Now the milk of magnesia is kind of fighting back, if you will, and you'll notice that the color change goes back to green here. And that's when the milk of magnesia has neutralized the vinegar. So there, it's neutralized it. And now the milk of magnesia has kind of taken back over in the solution and given us our blue color, which indicates that this is a basic solution. So in science, we use a lot of things to help us see things that we can't normally see. And indicator solutions are one of those. You can make indicator solutions at home using cabbage juice. Purple cabbage juice is a great indicator, and if you put it in things like soapy water or in vinegary water, you can see the color change there. That is one thing that you can try at home. Now I want to show you another example of a toroidal vortex, and I got one over here. So I've got in my little setup here, I've got a Lazy Susan, and a Lazy Susan is just a little turntable. All right, and on top of the Lazy Susan, I got this trash can, right? And this trash can has holes through it, mesh holes. And inside here, I have a heat-proof dish. And in that heat-proof dish, I've got a little alcohol. So what I'm gonna do is I'm gonna add a little fire in here, right? And you'll notice that the flames from the fire go up. Hot things tend to expand, and because this is sitting in a container, it can't expand horizontally, so it goes vertically, right? So it's expanding, it's becoming less dense, so it rises. So that's why hot things tend to rise and cold things tend to fall, all right? You can try this experiment at home if you want by opening your freezer door. If you open your freezer door, typically your freezer doors are on top of the refrigerator, and the energy will, the cold air will fall down on top of it. So what we're gonna do now with this one is I'm gonna give this a little spin, and you'll notice what happens here. I get a little tornado, a little fire tornado. This is another type of vortex, all right? As it spins around, you notice that the tornado rises up from the bottom. This is just like tornadoes form in real life. Warm air close to the ground interacts with cooler air falling from the top, and then a little crosswind will give it the toroidal vortex that we were looking at. So you can kind of see there our fire tornado. All right, so let me get this out of the way, all right? And we're gonna do another experiment here using some atmospheric pressure, all right? So here's my vase. And in this vase, if I ask you what's in this vase, you might tell me nothing, right? You might tell me that there's a vacuum in there, those kind of things. Let me help you out and show you what's in there. All right, so I'm gonna dump that out. So I've emptied out the vase. Now I'm gonna fill it back up. So now the vase is full of air. If this vase was full of dirt, it'd be really easy for you to understand what's gonna happen next. When I take this water balloon and try to put it on the vase and push it in there, it can't go in because the vase is full of air. But you can't see the air in there, right? If it was dirt, no problem, you'd be able to see it. That there's no way that the vase is gonna go down in there because the dirt is in the way. And unless we take some of the dirt out, the balloon won't be able to go in there. So there's air in there right now. I can't push it down in there. If I push on it too much, it's gonna pop. All right, but so what we need to do is we need to get some of the air out of there. And the way that we can do that is use what we just saw. We know that hot things expand, right? If we make the air inside this hot, it can't expand outwards, it can only go upwards. So I want you to notice when I take the hot air, when I take the water balloon and put it on top of the vase, notice nothing happens. There's no activity, it just sits there, okay? Now what I'm gonna do is add a little bit of hot air in there, and something interesting is gonna happen. All right, so this happens quickly, so pay attention. Remember that the balloon doesn't move when we put it on there when it's just cool. All right, so I'm gonna light this on fire. So you noticed that when I put the balloon on top of the flaming paper towel, that the balloon jumped up and down. That's because the air inside the vase is hot, it's trying to expand. It can only expand in one direction, and it pushes the balloon up out of the way. That's what causes the balloon to jump up and down. Then, after the air has expanded a little bit, some of the air sneaks out, but as the balloon falls back down, it seals the hole, which means there's a little less air in there than there was to begin with, which means that this is not completely full, which means that there was space in there for the balloon to go into. Also means that there's a little lower pressure inside the vase than there is outside. Since there's lower pressure inside than outside, the atmospheric pressure in here pushed the balloon down into the vase, which is pretty cool. That looks like magic, but remember, rule number 2, it's not magic, it's science. All right, let me show you another example of something that looks kind of like magic, but it's not really magic, it's definitely science. So what I've got here is I've got a watermelon, okay? And traditionally I would do this this demonstration with pumpkins, but it being the middle of the summer, it's hard to find pumpkins this time of year. So what I'm gonna do is I've carved this watermelon, all right? And I've got some of this chemical. This chemical is called calcium carbide. Calcium carbide will produce a reaction with water that makes a acetylene gas, and acetylene gas is explosive, right? So we've used calcium carbide forever. When we discovered that it would react with water, we used this in miners' helmets back when we didn't have batteries. The miners would wear helmets with a little flame that would poke up. You can go take a look at those miners' helmets and see that what they would do is they had a little bit of water that would drip onto some calcium carbide and create the acetylene, and then they would light it on fire and use it to light their way. So what we're going to do is we're going to take a little bit of calcium carbide and put it in some water inside of our Jack-o-melon. All right, and come in here. I want you to see what the calcium carbide looks like. It's this little black solid. It looks like graphite or maybe some lead or whatever. But this is going to react with our water and produce acetylene, and then we're going to get the acetylene to do some work for us. So I'm going to put it in here. All right, it's starting to bubble a little bit. All right, here we go. 3, 2, 1. And there we go. Did we carve our pumpkin? We did, we carved it, sort of. These pieces normally would come out, but you get the idea. So there is our Jack-o-melon. So what happened when I set the acetylene on fire, the acetylene decomposed into oxygen and carbon dioxide and a few other things. And those gases were hot, so they expanded. Well, they expanded until they ran into the sides of the watermelon. When they ran into the sides of the watermelon, they couldn't expand anymore except in the places where there were weaknesses. And you can see here that I carved some holes in the side of the watermelon in order to give it a space to expand out of. And when it expanded, it pushed out our pieces here, so it was able to do some work. I think that's a fun trick, and I'll do this one again for you guys in the fall with some pumpkins. It makes it even more fun. So let me show you another chemistry trick. This is one of my all-time favorites. All right. So in this is a graduated cylinder, right? We call it graduated because of the lines. These lines are called graduations, and it helps us measure the amount of liquid that's in there. All right, there's nothing in here right now. I'm going to add some of this stuff in there. This is hydrogen peroxide, right? This is 30% hydrogen peroxide. The stuff that you guys have at home is about 3%, right? So this hydrogen peroxide, you know, if you put it on a cut, it bubbles. Hydrogen peroxide decomposes or falls apart into oxygen. That's the bubbles that you see when you put it on a cut. Those oxygen bubbles kill off the bacteria, which is why it's a good antiseptic. All right, what we're gonna do is we're gonna use this to our advantage. We're gonna use some of the bubbles and make some interesting things happen here. Okay, so if you want to make bubbles, you gotta catch them. And so I'm gonna use some dish soap to catch our bubbles here. Put a little bit down in there. And I'm gonna add a little bit of food coloring to make it easier to see what's going on. I'm gonna go with green because I feel like it. So there's some green in there, all right. So hydrogen peroxide soap and green food coloring. All right, and then I'm gonna add some chemical that will bring all of the bubbles out of the hydrogen peroxide all at once. This chemical is called potassium iodide, and it's a catalyst. It makes the hydrogen peroxide fall apart and give us all the bubbles. So here we go. 3, 2, 1. So you can see what we've got going on here is something that my students used to call elephant toothpaste. It does kind of look like toothpaste being squirted out of a tube. You see the steam coming off the top? That is steam. This reaction is exothermic, which means it gives off heat. The steam is water, but there's also oxygen bubbles in there. So that's a pretty interesting reaction going on. This is a decomposition reaction. The hydrogen peroxide is falling apart into water and oxygen, and that's what's giving us the bubbles. And this foam that you see is really small bubbles, and I just think this is just one of my favorite reactions that I do. I've got one more of my favorites that I want to show you. All right, and this one is another magic trick. Again, remember, I'm not a magician, I'm a scientist. All right, so I've got this jar of really gross looking things. You may recognize those as pickles, all right? We make pickles by introducing vinegar and salt in a solution to our vegetables. And we use the pickling process to preserve the foods so that we could take them on long journeys and things like that before we had refrigeration. So now pickles, we've been making pickles for forever. All right, and what I'm gonna do with the pickles, in this case, I'm gonna use its properties of being an electrolyte to do something interesting. If you're an athlete, you may have heard of drinking pickle juice because it has lots of electrolytes and stuff like that, which is totally true. It's got salt and other electrolytes in there, which will help replace the electrolytes that you lose when you exercise. So what I'm gonna do with this though, is I'm gonna use that electrolyte property. When something is an electrolyte, that means it conducts electricity. So what I'm gonna do here is I'm gonna plug this in. By the way, remember rule number 1, don't try this at home. This is the most dangerous experiment that I do. And if you do this one incorrectly, it could really hurt you. All right, so what I'm gonna do is I'm gonna plug in this pickle and something interesting is gonna happen. All right, so zoom in there on the pickle. Here we go. 3, 2, 1. Takes a second for it to kind of warm up, but there we go. The electricity is passing through the electrolyte, through the vinegar and salt solution that's in the pickle, and that yellow color is the sodium that's in the vinegar solution. All right, and so we're passing electricity through our pickle, turning it into a light bulb. Oh, it smells gross in here right now. All right, that's one of my favorite ones. That one definitely looks like magic because, you know, I'm assuming you've never seen a pickle do something like that before, but it really is just science. All we're doing is passing electricity through an electrolyte solution, and that's giving us off our light there. Now, if we step over here, I'll show you one more activity that I've got. Oh, I do need a couple of things to help me out. All right, so I've got another container here, and you see in this container is empty of everything but air. So I filled it up with air, okay? Now what I'm gonna do is I'm gonna add a little bit of alcohol in there. And what I'm gonna do is I'm gonna fill this container up with alcohol vapor, right? And so I'm gonna take it and flip it around here. What I'm doing is I am evaporating the alcohol. You know, if you rub alcohol on your skin, you know, it turns your skin cool, and that is because the alcohol is evaporating off of there. It turns into a gas really, really quickly. So I don't want any liquid in there, so I'm gonna shake some of that liquid out, right? And now what I'm gonna do is I'm gonna use the alcohol vapor to do something interesting. All right, so I'm gonna take a little piece of paper here. I had trouble with this experiment previously, so hopefully this one will go well this time. Set it on fire. All right, are you ready? Like I said, I had trouble with this experiment before. All right, here we go. Whoa. So you saw what just happened there, right? You saw that we had alcohol vapor in there. The alcohol combusted and expanded. The only place that it could go was up, so it blew everything from the inside out. And you heard it go whoosh. We call this one the whoosh bottle, all right? And what you saw was the paper towel, which was on fire, being blown out by the expanding air. So that was the whoosh bottle, one of my favorites. Now I've got one more demonstration I want to do with some air, hot air for you. All right, and in order to do this, I'm going to set up a little target here. So what I've got is a little paper towel, and I'm just using this as a target. And I've got my Vortex cannon here. All right, so if you can see in the end of my trash can that I've got here, I cut a hole in it, right? This is just a regular old trash can with a lid on it. I've got a piece of string to help me hold it. All right, and what I'm gonna do is I'm gonna whack the end of my trash can here and aim it at my paper towel. All right, so when I do that, something interesting is gonna happen. 3, 2, 1. So now if I was a magician, I would say something like, oh, I'm gonna use the powers of my mind to push the paper towel off the table. You know, I'm not a magician though, I'm a scientist. So what did I really do? Well, what I really did was I used the air inside of my Vortex cannon to push the paper towel. When I whacked the end of the trash can, it pushes the air out through the hole in the end, causing a little vortex to form, and that vortex can travel a really long way. And what you saw there was the vortex interacting with the paper towel. Let me add a little smoke here, and that'll make it easier for you to see our vortex that's formed. So adding a little smoke from some movie magic, all right? And you'll be able to see a little bit better what's going on. All right, so here we go. 3, 2, 1. All right, I'm gonna blast one at you. You'll see the smoke ring coming at you. 3, 2, 1. So you see the ring, it's a spinning ring of air. And that ring is formed when the air in the trash can is being squeezed out through a smaller opening. The air interacts with the edge of the trash can and gets stuck, which causes it to slow down a little bit. So some of the air slows down, some of the air speeds up, but it's all stuck together. It's kind of sticky, and that causes it to spin and make that ring that you see. Now you've seen similar stuff, like the dolphins like to blow air bubbles like that. You may have seen somebody blow a smoke ring before. So this is one example of this, but this is my Vortex cannon. All right, and for my last trick that I got for you today, I want to show you something that I think is a lot of fun. This is a demonstration of Bernoulli's principle. All right, and Bernoulli's principle says that when air goes over a curved surface, the air has to go at the same speed. The air has to cover the same distance at the same time. So that means if you got air passing over a curved surface like a wing, or in this case like toilet paper, the air going over the curved surface has to go faster than the air going under the flat surface, which if the air on top is moving faster, that makes a low pressure area. So that means if there's low pressure on top, higher pressure on the bottom, that generates lift. So when I turn the leaf blower on, it's gonna blow air across the paper towel, across my toilet paper here. It's gonna create lift on the top, an area of low pressure up here, and then an area of higher pressure underneath the toilet paper, and well, you'll see what happens. Here we go. 3, 2, 1. So there's my toilet paper cannon using Bernoulli's principle. That's my last demonstration for you today. I hope you've enjoyed a little bit of iScience. I hope you have been encouraged to study science and find out all the cool things that go on in our world and how you can apply them to your life. Thanks for joining me today, and keep on doing science. Remember, rule number 1, don't try it at home, and rule number 2, it's not magic, it's science.